Good morning. Now, this is our last class on wave motion. Along with this video, as usual, I will upload a few solved problems and some short answers and essay type questions. Then, one thing that you have to notice that I will be uploading an assignment also along with this video in LMS, and that assignment is nothing but just 5 problems, okay, from this chapter wave motion. So do those 5 problems and submit it as usual on or before 10th July. Okay, so let us begin our class. Now today what we are going to learn is about transverse waves in structured strings. Now we know what a transverse wave is. What is a transverse wave? Transverse waves are those waves in which particles vibrate perpendicular to the direction of wave propagation, right? Now here we are going to discuss about propagation of such transverse waves in strings, where particles of the strings, as I said, they vibrate at right angles to the wave propagation. Now here a string actually refers to a wire or a cord with length large compared to the diameter. So string means nothing, it is just a wire, and it is assumed to be uniform, flexible, and that string is stretched between two fixed points. So that string will be experiencing large tension. Okay. So you have got a string which is nothing but a wire, and what are the peculiarities of that wire? Its length is large compared to diameter, then it's uniform, flexible, at the same time it is stretched between two fixed points, so naturally that string will be under high tension. Now here our aim is to obtain an expression for the velocity of transverse wave developed in the string. Okay. For this, what we do is the string that I have set before. Okay, that particular string is stretched between 2 points, say P and Q. So you have got 2 points P and Q, and you are stretching that string between those 2 points P and Q, and let capital letter T be the tension experienced by the string. Now here we assume that string is fixed in the x direction and it is made to vibrate in the y direction. How you develop vibration? You just pluck the string at its center O. Then vibrations will develop in the string, and we assume that those vibrations are in the y direction, whereas the string is fixed in the x direction. Now we already made an assumption that the string is flexible. Because of that reason itself, the tension which is experienced by the string will be the same at each and every point of the string. So since the string is flexible, it is experiencing the same tension at each and every point. Now our aim is to calculate or to evaluate the component of tension T. Okay. For that, just consider a small element, say AB of the string. That is, you have got a string. In order to evaluate the component of tension, you are considering a small element of the string, and let that small element be named as AB. Let the length of that small element be delta x, and let it be at a distance x from the point P. Everything is shown in the figure given below. Now let y be the displacement of the string. Okay. So they have written in very simple sentences that you can easily understand. So I am not explaining it again. Now here A dash B dash is the displaced condition of the element AB, and phi plus delta phi and phi are the inclinations of the tangents at A dash and B dash. Okay. So if AB is the original element of the string, and when it is displaced, that displaced element is represented as A dash B dash. Okay. Now what is phi plus phi dash? It is the inclination of the tangent at A dash, and phi is the inclination at the tangent B dash. Now we are going to resolve the tension T at those 2 points, that is A dash and B dash. That is, we are resolving it into horizontal and vertical component. Okay. So the horizontal component is represented by Tx and is given by T cos of phi plus delta phi minus T cos phi, and the vertical component Ty is equal to T of sine phi plus delta phi minus T sine phi. Here just note that horizontal component means cos theta, vertical component means sin theta. So it is actually the displaced portion minus original portion. Okay, this is the inclination at A dash, inclination at B dash. Okay, so again displaced minus original. This is also displaced minus original. So you got the two components, horizontal component and vertical component. Now we make some assumptions. That is, we assume that phi and delta phi are very small. So if that is the case, then what happens to cos phi plus delta phi given in equation 35? It will reduce to cos phi. Then what about sin phi plus delta phi in equation 36? It will reduce to phi plus delta phi. Again, the sin phi, which comes under equation 36, will reduce to phi. So these are some mathematical assumptions that we make by considering that phi and delta phi are very small. So by making these assumptions, our equations 35 reduces to Tx equal to 0, and equation 36 will reduce to Ty is equal to T delta phi. There is nothing to understand. You just substitute these values. Okay, instead of cos phi plus delta phi in equation 35, you write cos phi like that. So you just substitute those values. So on making these assumptions, or by substituting these assumptions in equation 35 and 36, those equations will reduce to Tx equal to 0 and Ty is equal to T delta phi. So this means that horizontal component cancels each other because Tx is 0, right? So horizontal component cancel each other, and what remaining is only the vertical component, that is Ty, T delta phi. Okay. Now for small angles, phi is equal to tan phi. So that equation 36a can again be written as Ty is equal to T delta of, instead of phi you are writing tan phi. So that is nothing by T delta of tan phi is written as dy by dx, because that actually indicates the slope. Slope is always y by x, right? That is why we are writing tan phi as dy by dx. See, here they have written dy by dx is the slope of the string. Next, equation 37 can again be written as Ty is equal to T, instead of delta you are writing d by dx of delta x. Okay, dy by dx is kept as such. Instead, this delta is given as d by dx of delta x. Okay, so just make that replacement instead of delta. So that is t is kept as such, delta is written as d by dx of delta x. dy by dx is kept as such. So on expanding, what happens? This becomes t is equal to d square y by dx square delta x. This is nothing but the restoring force which is acting on the string. What is restoring force? A force that tries to bring back the string to its original position or equilibrium position. Okay, so equation 38 is nothing but restoring force acting on the string. Now if mass per unit length of the string is given by the letter small letter m, then the element delta x has a mass m delta x, right? Now if the acceleration of this element at the displacement y is d square y by dt square, okay, that we know. Acceleration is represented, velocity is dy by dt, acceleration is d square y by dt square. Okay, so you make for acceleration it is d square y by dt square, and the mass of the element delta x is m delta x. Okay, now using those two conditions, in equation 38, the equation of motion of the string will finally reduce to, that is here, equation of motion. See, we told that this one is the force, restoring force acting on the string, right? What is force? Force is mass into acceleration. Here our mass of that element delta x is m delta x, right? What is acceleration? D square y by dt square. So this term is actually this one, right? So they have written right like that, m delta x d square y by dt square is equal to t d square y by dx square delta x. So from that, d square y by dt square is nothing but t by m d square y by dx square. Now you just compare this equation with the standard wave motion equation. What is the standard wave motion equation? D square y by dt square is equal to d square y by dt square is equal to v square d square y by dx square. This is the wave equation, right? Now they are asking you to compare this wave equation with the equation 39, and what you can find, LHS is the same, right? RHS is also same. So t by m is equal to v square, that is velocity square is equal to t by m, right? So what will be the velocity v? It will be root of t by m. That is the velocity of your transverse wave developed in the string. See equation 40. So now you have derived the expression for the velocity of transverse ring developed in the string. Now from this you can note one point, that is this velocity depends only on the tension T and mass per unit length of the string m, because there is no other term in equation 40, only T and m. So velocity of transverse wave v depends only on tension developed in the string T and the mass per unit length of the string m. Okay, now just a so this is an important essay, that is what is meant by transverse wave. Derive an expression for the velocity of transverse wave. Then next one is a small section, the last one, modes of transverse waves in string. That is, you just read, consider a string of length L fixed between 2 points. As already said, when it is fixed between 2 points, naturally that string will experience a tension T. Now we are displacing the string to one side and then release it. Then it will execute transverse vibration. Now we have already said that the ends of the string are fixed. So the transverse wave thus developed will reflect from one end to the other end. So standing waves are formed. When are standing waves formed? When one wave goes to one side and another wave from the opposite side comes to the other side. So a standing wave will be developed. Now if the string is vibrating in a loop, what happens? If that is the case, then at the end of the string you can see a portion called node, somewhat we have discussed in our first class, and at the same time in the middle you can see certain portions called antinode. Now in that case the frequency of vibration is given by 1 by 2L root of T by M. L is the length of the string, T is the tension developed in the string, M is the mass per unit length. Okay. Now here that frequency nu 1, it is given a name, that is fundamental frequency or first harmonic of the string. So that is the fundamental frequency. Now the vibration of the string into one segment is called fundamental mode of vibration. So this one is the fundamental frequency nu 1, and what is fundamental mode of vibration? It is the vibration of string in one segment, that is the fundamental mode of vibration. If the string vibrates in two segments, then it will be called second mode of vibration. So if the string vibrates in one segment, it is called fundamental mode of vibration. If the string vibrates into two segments, then it is called second mode of vibration. So if you are considering second mode of vibration, the frequency in that case will be different. That is given by 1 by L root of T by M. Okay. Then if the string vibrates into three segments, then it is called third mode of vibration. In that case, the frequency is 3 by 2L root T by M. Okay, that is a difference. So here, if the string is vibrating in a loop, then you will notice notes and antinodes, and that frequency of vibration is called fundamental frequency. And in such cases, the string vibrates only in one segment, and it is called fundamental mode of vibration, and it is given by 1 by 2L root T by M. Now, if the string vibrates into two segments, then it is called second mode of vibration, and it's given by 1 by L root T by M. If the string vibrates into three segments, then it is called third mode of vibration, and is given by 3 by 2L root T by M. So here the frequencies nu1, nu2, the frequencies nu2, nu3 are called a second harmonic. Nu1 is nothing but fundamental frequency or first harmonic. Okay, but nu2 is called second harmonic, nu3 is called third harmonic, and so on. Now second harmonic is also called first overtone, third harmonic is also called second overtone, and so on. So from this paragraph you are getting some definitions, that is what is fundamental frequency, what is first mode, second mode, third mode of vibration, what is second harmonic, third harmonic, and so on. Okay, so from here you just need to study the definitions, but this one is an essay. Okay, so with this we have completed wave motion. So once again I remind you that 5 problems from this wave motion will be uploaded in LMS as your assignment, and you have to submit it on or before 10th July. Okay, now the possible essay questions from this unit are: derive the differential equation of wave motion, then comes what is plane progressive wave and derive the expression for its energy density, then what are beats, discuss the mathematical treatment of beats, and finally the one that we have discussed today, that is what is transverse wave, and to derive the expression for the velocity of transverse wave developed in a stretched string. Okay, so for today this is enough. Thank you.